Hi folks, in this next part of this week's lesson, we are going to be trying to define yet another operation on vectors, okay? And it's another operation that we're going to consider a product. So this was that other product that I was alluding to previously. And the goal for this one here is we're going to operate on any two vectors, and we want the resultant to produce a vector. Okay, so already we see something different from the dot product, as the dot product produced a scalar quantity, and the vector that it produces needs to be perpendicular to the original two vectors. Okay, so I'll try to draw this in 2D here. It'll be a bit tough, but I'll try to show you a 3D model later on. So let's say I take any two vectors, say this is u and this is v, and the goal is to come up with some vector set called w, which is perpendicular to both of these vectors. So I'll try to draw it so that we can see that it's perpendicular to both the original vectors. Okay, so you have to see this sense of perspective. All right, let me see if I can show you something. So I'll bring this as high up as we can. Okay, and so let's say I have these two pens representing two vectors. Okay, notice here, placing them tail to tail. And what I'm looking for is I'm looking for some third vector here, which is perpendicular to both of the original vectors. Okay, so perpendicular to both vectors u and v. Now, one thing I hope you notice is that this is not going to be one unique vector, because if I take a vector that's longer but in the same direction, well, that's also perpendicular to both vectors. If I take an even longer vector, okay, that's in the same direction as that original one that I showed you, it's also perpendicular to both vectors. And in fact, you can see that if I take a vector in the other direction, so opposite, if you can kind of see it there, okay, it's also perpendicular to both of these vectors. All right. So clearly there's more than one possible vector that's perpendicular to the original two. All right, we're going to choose one of them to represent this operation, but any scalar multiple of that vector will also be perpendicular. Okay, so this kind of gives us an idea that while our operation is going to produce one of these vectors, there's actually infinitely many possibilities. Okay, so now we're not going to prove how to get this vector. I'll just give you a sense as to how you would do it. Okay, and if you're interested, you can check up in the book and it shows you how it does that. So I'm looking for this vector w, and the condition on this vector w is it has to be perpendicular to both u and v. And of course, we know that if two vectors are perpendicular, their dot product is equal to 0. So the way you start this process off is you define the vectors, say x1, y1, z1, x2, y2, z2, x3, y3, z3, and you want to solve the equation u dot w is equal to 0 and v dot w is equal to 0. All right? And in fact, when you try to solve this, not surprisingly, you get infinitely many possible answers, but all those answers are scalar multiples of each other. And what they did is they decided on one particular vector that's going to represent what we call the cross product. All right, so we had the dot product or scalar product, which produces a scalar quantity, and now we've got the cross product or vector product, which produces this vector quantity. And what's special about this vector quantity is it's perpendicular to the original two vectors. All right, so I'm going to give you the definition here. So u cross v, okay, now here we'll assume that u is equal to x1, y1, z1. So we want to define it as generally as possible. And then vector v is just going to be equal to x2, y2, z2. Okay, now by the way, this is going to be an algebraic definition. Algebraic because it's going to be composed of just the components of the two vectors. Okay, and it's a product because it's going to involve taking multiplications. Okay, now notice I left myself lots of space here because it's quite a long definition. All right, so let's go. We have y1 z2 minus z1 y2. That's the x component. The y component is z1 x2 minus x1 z2. All right, and then lastly, the z component is given by x1 y2 minus y1 x2. And that is the definition of the cross product. So this vector here will automatically be perpendicular to both of these two vectors. Now, if you're telling yourself this seems like a fairly complex equation or definition to memorize, well, you'd be right. This is not quite as, you could certainly come up with some memory tricks around that. I'm sure you could, but this is certainly not as nice as addition, subtraction, or even dot product, which is relatively simple. All right. So there's this whole bunch of ways, whole bunch of memory tricks that people use to remember this. I'm going to show you my, the one that I personally use, but the textbook has a different one, and you can look up online. There's tons of different memory tricks you can use to remember this. All right, I'd pick one and I would use it all the time. Okay, so this is the one that I use. Is I take my two vectors and I place them one on top of the other. So I have x1, y1, z1. Okay, and then here I have x2, y2, z2, okay? And then what I do is I rewrite the x components to the right of z1, so x1 and x2. Now, I'm hoping you might have noticed something interesting about this formula here, because look at the x component of the cross product. There's no x components from the original vectors. And same thing here, the y component, there's no y's. Z components, there's no z's, okay? So it's one of the ways that you can help you remember. So here, if I want to do u cross v, I want you to see the little trick that I use here is look at the x component, okay? Well, remember, the x component doesn't have any x's, so I'm going to block off that column, and look what we have here. If I do this cross multiplication, so y1 z2 minus z1 y2, and I subtract them. And lo and behold, what do I get? Exactly the x component. Okay? Then I block off the y column to do the y component. And look what we have. The same cross multiplication gives us what we need. z1 x2 minus x1 z2. Okay, exactly what we have there. This gives you the y component. And then lastly, if I want the z component, I'm going to block off the z component and work with these two columns. And look what we have, x1, y2 minus y1, x2. Exactly there. And there's your z component. Okay. And so this is the trick that I use to calculate the cross product. Like I said, take a look at a couple of them, but I would definitely use one of those instead of trying to memorize this expression here. All right. So we're going to confirm that this works, that this indeed does give us a third vector that's perpendicular to the original two. But before we do that, I do want to talk about the fact that notice how I worked with these two vectors, 3D vectors. So one would think that there would be a version of the cross product in 2 dimensions. Well, let's take a look here. So let's say I'm in 2D, okay, and say I've got this vector here, say that's vector u, and say that vector there is unit v. And let's see if we can come up with a third vector that's perpendicular to both in 2 dimensions, okay? Well, this is when I realized that if I try to find a vector that's perpendicular to u, so something in this direction, okay, and you can see there's infinitely many vectors that are going to be perpendicular to u, it's not going to be perpendicular to v. And if I try to determine vectors that are perpendicular to v, they're not going to be perpendicular to u. And this is where you realize that unless u and v are in the same direction, there's no way to find a third vector that's perpendicular to both. So the cross product, okay, is quite a different operation because it's the only operation that's only defined for 3D vectors. There's no cross product for 2D or 1D vectors. All right. Now, you might sort of ask yourself, well, why would we define something that's only valid for 3D vectors? Well, remember we said sometimes we define things because we need them to perform a certain task. And the task that we need is in 3D. It's going to be useful for us to have this third vector, which is perpendicular to the original two. All right, so let's take this here, and I'll leave that up, and let's take a look at a cross product, and we'll confirm that what we get is indeed perpendicular to the original two vectors. So I'm going to use my trick here. So 2, 3, -4, and then here -6, 3, 8, and I'll recreate the x's here, 2 and -6. Okay, so if I want u cross v, okay, let me go ahead and do that. So it's going to be, hide the x, so 24 minus -12. So again, it's one of these things where for now, I'm going to write it all out. Eventually, you're probably going to stop writing it out or just do it in your calculator if they're big numbers. So here we're going to have -4 times -6, so 24 minus 2 times 8 is 16. Okay, and then lastly here, we'll do these two, 6, okay, minus -18. And so our final answer here is going to be the vector. Well, 24 plus 12 is 36. 24 minus 16 is 8. And 6 plus 18 is 24. So this vector here I am claiming is perpendicular to both of these two vectors. So let's test it out by using the dot product. So let's take the dot product of 36, 8, 24 with the first vector, 2, 3, -4, and let's see what we get. So 36 times 2 is 72. 8 times 3 is 24. Okay, and then here 24, so this is 80 plus 16, so minus 96. And let's see, what's 72 plus 24? Hey, that's 96 minus 96, 0. So this vector is perpendicular to 2, 3, -4. Now let's test it with the next vector, -6, 3, 8. Okay, and here, well, this one's a little, the numbers are a little bigger, so I'm going to decide not to do that one in my head, and let me use my calculator here. So we have 36 times -6, okay, plus 8 times 3, plus 24 times 8, and that's not equal to 0. So let me check that one again. I'm pretty sure this should work, so let me make sure I wrote everything else correctly. -6, 3, 8, and 36, 8, 24. So let's try again. So we've got 36 times -6 plus 8 times 3 plus 24 times 8. And there we go, we get 0. I must have typed something in incorrectly into my calculator. All right, so just a bit of not a proof, but definitely, an indication that we're not just making this up. All right, now here it asks you to determine 3 other vectors which are perpendicular to both u and v. And notice I left very little space, and that's because remember what we talked about. She said, well, this vector is the cross product of u and v. It represents only one vector that's perpendicular to both. Any scalar multiple is also going to work. So here, any scalar multiple of u cross v. Okay, so let's put a few. Well, let's multiply them all by -1. Let's say -36 and -8 and -24. That works. Okay, I can multiply everything by 2. 72, 16, 48. Okay, or you know what? I could probably write this in a much simpler way. Okay, these things all have a common factor. In fact, they have a greatest common factor of 4. So if we divide all of them by 4, so in other words, multiplied by 1/4, we end up with 9, 2, 6. okay? And we could write many, many more, all right? So the main thing to keep in mind is what the cross product is here for, what it provides for us. And what the cross product provides is a vector that's perpendicular to the original two vectors, okay? That's its purpose. Okay, now sometimes you're dealing with a whole bunch of other vectors, and this is where, you know, the cross product, like the dot product, has a whole bunch of properties. You know, let's take, in fact, these two here. You know, if I take u cross 0, so x1, y1, z1, any vector with 0, 0, 0, okay, and let's use my trick here. Well, we realize that all the multiplications would all produce zeros. So that's just going to be the vector 0, 0, 0. Okay, probably not too shocking. Okay, let's take, say, u cross v. U cross itself. Let's see what happens. So I won't use the ones here since they're the same vector. So x, y, z, and then let's cross it with x, y, z. Okay, well, let's do u cross u. Let's see what happens. Well, we have yz minus zy, 0. Let's do, whoops, I forgot these here, zx minus xz. Those are the same. So again, 0, and xy minus xy, 0. So it also produces 0. Now, that should maybe not be too surprising, because if I try to cross a vector with itself, well, it's the same vector. And that's when I realize my perpendicular vector is not just in any one direction. I have infinitely many directions, okay, that give me a vector that's perpendicular to both. So not surprising that the cross product would not be helpful, because you don't want it to provide any particular direction, okay? But what about this one here? Commutativity. Does it matter what order I go in? Okay, let's test here. x1, y1, z1, okay, and x2, y2, z2, x1, x2, and let's see what happens. So I'm just going to write the first component, just the x. I think we'll see what's going on here just with the x. So let's go in the order u cross v. So you see that the vector u is on top, v is at the bottom. So let's just do that first. And well, we get, of course, oh, no, sorry, we're doing the first one. We're doing the x component. So we're hiding the x. So we're doing y1, z2 minus z1, y2. And so on and so forth. Well, let's see what happens when we just switch the order. Let's put the v on top and the u on the bottom. Okay, and now let's do v cross u. So just switch their order. Okay, well, let's see what we have. We have y2z1 minus z2y1. Okay, well, that's just the x component. And this is where you see, well, wait a minute, look at the first term here is the same as the second term in the original one, and the second term here is the same as the first term in the original one. But because this is a subtraction, we know that you're not going to get the same value, but when you flip around a subtraction, you're just going to get the negative. So what we have is that u cross v and v cross u are not equal. So it's not commutative, but they are negatives of each other, and so that's what we call anti-commutative. Okay, so later on we'll see that there's a whole bunch of other characteristics that they have, but probably this is the one we might use once in a while, is the fact that u cross v and v cross u are negatives of each other, or their opposite vectors, okay? So here's the last thing we're going to look at, because you'll notice that everything we did here involved working with these vectors algebraically. And there is a geometric version of the cross product, okay? So let me just give it to you, and then we'll look at it a little. So here, U cross V. Now it's interesting because the geometric definition is not directly the vector U cross V, okay? It's the magnitude of this vector. And the magnitude of this vector, and I think you're going to see that this looks very similar to something you've seen before, well, it's still the magnitude of U times the magnitude of V. So we're multiplying the magnitudes, again, why we call it a product, okay? But instead of multiplying by cos theta, we multiply by sine theta, all right? So now the question is, well, this gives us the magnitude, but U cross V is a vector. How do we calculate the direction given this geometric definition? And this is where, I'm going to bring this out again, this is where we use what we've seen before, this idea of the right-hand rule, okay? So remember the right-hand rule, the way it worked for the axes, okay? The right-hand rule worked that you point your fingers in the direction of X, you curl towards the direction of positive Y, and your thumb was the direction of Z, okay? And it works in a very similar way. So here, if we have our two vectors, U and V, okay? So let's say this vector here is U and that vector is V. So what I do is I point my fingers in the direction of U, I curl towards V, and then my thumb gives me the direction of the cross product, okay? So V, U, direction of my vector with my right hand. But now this kind of is, if you think of it going the other direction, what if I do V cross U instead of U cross V? Well, look what happens. If I place my fingers in direction of V, curl now towards U, look where my thumb goes in the exact opposite direction as before. So U cross V, I'm going that way. V cross U, I'm going this way. So that kind of demonstrates the anti-commutativity of the vectors, of the operation, okay? So what we're going to do here is, again, we're not going to prove this. The proof is, a little long. In fact, the book does a proof, but they kind of skip some really tough steps, okay? So what we're going to do is we're just going to show that these two definitions give the same magnitude, okay? So we'll stick to the magnitude. So let's start by the algebraic definition. Well, we already have the cross product of these two vectors. If we look back, the cross product of these two vectors we had already found is 36, 8, 24. So I'm not going to redo that one here. So let's do 36, 8, 36, 8, 24, and let's find its magnitude. Okay, so this is the start with the algebraic definition. And so here, let's get our calculator here. So the magnitude is going to be the square root of the individual components squared added together. So 36 squared plus 8 squared plus 24 squared is equal to 1936. So square root of 1936. And let's see if this happens to be a nice square root. Oh, it's exactly equal to 44. Okay, that's nice. Okay, so there's our magnitude. So let's now use the geometric definition and see if we get the same value. So the geometric definition says the magnitude of U. So the magnitude of U is going to be 2 squared plus 3 squared plus negative 4 squared okay, times the magnitude of v, which is going to be negative 6 squared plus 3 squared plus 8 squared, okay, times the sine of the angle. This is where, in order to use a geometric definition, we're going to have to determine the angle theta. But luckily, we have the dot product to help us determine the angle. Remember, we can use the dot product, u dot v equals magnitude of u times magnitude of v times cosine of theta. So let's do u dot v. So 2 times negative 6 is negative 12. 3 times 3 is 9, so plus 9. And then negative 4 times 8 is minus 32. Equal to, well, we already found the magnitude of u. So let's just add this together here. So what do we have? We have 4 plus 9 plus 16. Now we could have done that in our heads, but that's okay. 29. Let's do magnitude of v here. Okay, 6 squared is 36 plus 9 plus 64, 109 times cosine of theta. So theta is just going to be equal to cos inverse of, what do we have here? Negative 12 plus 9 minus 32 is negative 35 over root 29, root 109. Okay. So what do we have here? We've got inverse cosine of negative 35 divided by square root of 29 times, oops, I forgot the square root, times the square root of 29 times the square root of 109. And what do we get? We get 128.5. Okay, so let's now put this in here. So again, this is just root 29, root 109, sine of 128.5. And let's see if we get 44. Okay, so here, let's do that here. We've got root 29 times root 109. Oh, sorry, root 29 times square root of 109 times sine of 128.5, and look what we get, 44. Okay, so this goes to show, or at least it's not a proof, but certainly shows that it makes sense that these two definitions, okay, the algebraic one that we used before and the geometric one that we just defined now, give you the same answer. Now, more likely than not, you will be working with that algebraic definition. This is the one that's going to definitely come in most handy. All right. So before we leave this section here, okay, there's a lot of other applications to the dot product and the cross product, which we're not going to be going through here, especially in terms of physics. So some of you are, have taken physics or might be doing some physics next year. You might want to look at the full course lessons on some of the applications of dot product and cross product. All right, that's it for now.